Hey, good morning, everyone. So welcome to Microsoft's Research for Industry lecture series. I'm your host today. John Lemon. I'm a Power and Utilities leader for Azure Global Engineering. And before we get started, I'd just like to take a note on the screen about we'll have a question and answering session here. So you can type your questions in the live team sessions, and going to upvote the questions you'd like to hear about and sort the questions based on the most liked. And so, you can submit your questions via live stream as shown here on the screen. And we have a very exciting topic today. Our guest speaker today is Professor Warren B. Powell. He's Professor Emeritus at Princeton University and the Chief Analytical Officer at Optimal Dynamics. He's the founder and director of Castle Labs at Princeton, and this Castle Labs manages over 70 grants and contracts with government agencies and leading companies which are motivated to develop models of algorithms and freight, logistics, energy systems, and all kinds of other industries. And he's created a new field that's called Sequential Decision Analytics, and he's going to discuss this today. And he's Professor Warren has been a prolific, publications and over 250 publications, written 2 books. He's currently working on a new book called Reinforcement Learning and Stochastic Optimization, a unified framework for sequential decision making. And today, without further ado, we have a full time slot for him today. So without further ado, I'd like to introduce his talk, Sequential Decision Analytics, a unifying framework. So Professor Powell, please share your screen with us. Thanks.
I'd like to thank everybody for the opportunity to present to Microsoft. John, I appreciate the introduction. I'd also like to express my appreciations to Piyush Kumar, who originally contacted me and set this up. So what am I going to talk about? I'm going to talk about sort of almost everything. This is freight transportation, manufacturing, and logistics and supply chains. This is energy and health and e-commerce and finance. In other words, I'm sort of interested in all of these activities that sort of define human processes. Now, behind all of these are flows of information and decision making. Here's a number of control centers, and these are where the information decision making is highly concentrated. And I think it's actually useful to think of this process where information comes in and people make decisions and they're trying to make a better process, similar to an automotive assembly line. This is Tesla's, where the chassis goes down and robots act on the chassis to make it a better car, make it transform it into something useful. What we want to do is make decisions, and we have a number of goals and objectives, and these could be reduce cost and increase profits. Maybe we want to reduce COVID deaths or increase the yield of a manufacturing process. Maybe I'm into improving employee retention. Now, in order to improve performance, you've got to make better decisions. And that leads us to the first step, is what decisions are you making? Now, this seems obvious because there's some problems where the decision is obvious. What route do I make to a network and what stocks do I trade? And then there's a lot of complex problems like supply chains or the COVID pandemic and opioids and these more complex problems where people know what they want to achieve. They don't know how to achieve it, which is another way of saying they don't know what decisions. Second step is, how do we make effective decisions? And hopefully somebody in the tech sector will be saying, well, wait a minute, that seems like we need to turn to artificial intelligence. So let me first pause a little bit, because I see, and I'm sure everybody, especially on this call, is seeing, there's a lot of misuse of this term artificial intelligence. If you go to computer scientists who work in this field, it used to be that they would say, well, this is making computers behave like humans, because human decision making and behavior and intelligence was sort of viewed as the high watermark. But recently we've started to say, no, we want to make computers smarter than humans. If you go back to the 60s and 70s, we had rule-based AI, like if you're eating red meat, then drink red wine. But as you got into more complex things like health, where you have, oh, it's a male over 60 with high blood sugar, you have all these conditions, you'd have this explosion of settings before you'd say, here's the treatment. 1990s, optimization, specifically deterministic optimization, large-scale linear and integer programming really exploded. Now, this field had been emerging, had been worked on since the 1950s, but suddenly it became very visible. Companies doing optimization exploded in stock price, but then they started to try to apply it to the really complex problems like a supply chain, and suddenly it didn't work anymore and it sort of died down. So in the early 2000s, machine learning became the new AI. Everybody said you're doing AI really meant machine learning, and they specifically they meant neural networks. Now, a few years ago, this field called reinforcement learning emerged because it was helping people play chess and Go and control robots. And then we can sort of ask, what's next? What's going to happen in the 2020s? And I'm going to say it's sequential decision problems. This is where we need to make decisions over time as new information arrives. And what I'm going to do in this talk is to unify 15 distinct fields that deal with dynamic decision making, and I want to roll this into a field that I'm going to call sequential decision analytics. So in this talk, I'm going to start by introducing the 5 layers of intelligence, but let me draw your attention to the very bottom bullet. This is where I'm going to make the proposal that we need a new educational field, and I'm actually going to hope that companies like Microsoft can help push this forward. So let's start with the 5 layers of intelligence. Now, we want to get to the top layer, decisions, but to be quite honest, you have to understand the first 4 layers before you can start talking about decisions. So let's go ahead and start with information acquisition and storage, because this is a big deal. This is keyboard entry and barcodes, RFID chips, GPS trackers, image sensing, speech recognition. These are the sensory devices that we use so that we know the environment. Think of the analogy of touch and feel with smell and taste with humans. Now, of course, as you sense this, you have to store this information. So we've had this amazing evolution of data storage technologies. Today, the high watermark is the cloud. Everything that comes into a computer seems to vanish into the cloud somewhere. And that's not much value without the powerful software that allows us to access and manipulate this. So now we have information stored around various storage devices. But we have to share it. We have to communicate. So communication, I mean, I could go back thousands of years, but let's start with the lowly payphone and emerge through the internet and satellite communication, cell towers, and eventually we're, maybe even this year, we're going to start working with the SpaceX's Starlink system. And of course, we cannot forget that amazing device called the smartphone, because this is what allows us to be in the face of individual people. Now, even this is not enough. When companies operate, we have all this data that can be shared, but if I want to know where my product is so I can plan when it's going to arrive, companies started to emerge to say, look, you know, you don't know where your package is, so we're going to provide that for you. And companies like Fork Heights and Project 44 allow a company to say, where's my package? And they'll say, oh, it's on this cargo ship, it's on this boxcar, it's in this truck. Now, you have to at some point acknowledge that the issue of security is there. And I'm just going to say, and I have to say the word blockchain, but I'm just going to say, I'm not going to do anything with this. There's people who are much more skilled in that area than I am. So now we get to transactions and execution. So this was a major plateau, ERP systems and transportation management systems. This is where computers started to do really useful stuff, accounting and billing and order tracking and inventory management and driver tracking. Now, behind all this, so we have the computers doing all this very low-level decision-making and calculations, whatnot, but this is being used by people processing this information and making decisions. Now, the next step up is learning. So now we start getting to the types of intelligence that are on our radar screen today. Now, I tend to view machine learning as taking information that we do know to estimate something that we do not know. How will the market respond to price? How long will the order take to arrive from China? How many people are going to need hospitalization for COVID-19 next week? And how much energy will the wind farms generate this afternoon? I like to think of learning as coming into 4 broad categories. Pattern matching. Is this a flower? If it is, what type of flower? Somebody's logged into the internet. Oh, maybe this person wants to buy a pair of sunglasses. Maybe I want to estimate how an increase in the price will affect market demand, or what is the condition of a piece of equipment. And finally, the classical problem, here's past prices and demands and weather, and I want to predict the future. Now, whatever you're doing in machine learning, you're going to be using tools that fall into one of these three overlapping buckets: lookup tables, parametric models, non-parametric models. And I hope somebody's saying, well, wait a minute, where's neural networks? There it is. Neural networks fall between parametric and non-parametric. Basically, shallow neural networks are considered parametric models, and deep neural networks are considered non-parametric. By the way, it took me years to get the statisticians to nail that one down. Now, let me just say a couple words about neural networks, because I've run into people who think a neural network can do anything. So neural networks are first of all fabulous at pattern recognition, facial recognition, voice recognition, handwriting. Now, people overlook the fact that these are deterministic problems. There's always a correct answer to whose face, or what is the person saying, or what did they try to write. And in order to train the neural networks, you're going to have people saying, this is what the face is. Here's a X-ray image of skin tissue. Is there cancer there? Well, the way that gets learned is by having tens of thousands of images classified by radiologists. Now, you have to understand that neural networks do have difficulty, first, capturing problem structure, and B, handling noise. So it's not the panacea that a lot of people try to make it, but it was a powerful breakthrough. So now we've gotten to that top layer. We move pretty quickly here, but I do want to emphasize those 4 layers are important, and sometimes people forget about those. I'll come back to that later. So decisions. So we saw all of these great activities, and I'm sure that you can fill in with images of things that I haven't included here. Behind all these activities are decisions. And every one of these boxes has a choice that somebody has to make, usually by a human, but it could be done by a computer. And a decision always implies that there's a choice, and there's more than one choice, which means one of the choices should be best. Now, I can classify decisions into 3 broad categories. Decisions that act on physical resources, managing inventories, assigning drivers and loads, scheduling nurses and energy generators. We have financial decisions such as pricing, insurance, and managing investments, and hedging contracts in case the ship arrives late. And then there's the informational decisions of sending and receiving information, which is a decision in and of itself. Marketing and advertising, which is sending information to the market. Running experiments in the lab or the field, or testing drugs. Now, there's 3 important time frames to recognize. We have strategic planning, such as how many nurses should I have? Which supplier should make a part? Where should I locate facilities, and how large should they be? There's tactical planning decisions like, if I'm a trucking company, should I accept a load now to move a week from now? Should I place an order from China that'll arrive in 3 months? Or what pricing and marketing strategy should I use in the next quarter, given that sales are down right now? And finally, we have the real-time execution decisions. Which driver to assign to a load now? What bid to place on an ad to maximize ad clicks? What drug to prescribe for the patient right now? Now, each of these we can divide in the following way. Strategic decisions can be thought of decisions where we have to simulate decisions in the future that do not depend on the state of the system now. It's far enough out in the future. Tactical, I use the word tactical because these are used by different people in different ways to mean we have to simulate decisions in the future that do depend on the state of the system now. And real-time decisions is where I'm going to make a decision now, but I may need to simulate decisions in the future that capture the downstream effect of that decision made now. Now, let's also not forget the decisions are made at all levels of the organization. I come from operations research, which is closely associated with the field of industrial engineering, where there's a lot of focus on the factory floor, scheduling the machine. But middle management has great decisions. Maybe I'm not scheduling the person, but maybe I'm setting their performance metrics or performing inventory planning because the inventory will arrive well in the future. But let's not forget about the C-suite decisions, the top strategic decisions. All of these are great decision problems. Now, let me take a look at this very specific problem, deterministic optimization. And what we're going to do is look at the problem of airline scheduling. Now, that math, I don't know how many people listening to this talk understand that math, but there's a lot of people who are trained in that math around the world, all with the exact same notation. I don't care if you're from Europe or the US or China. This is standard notation, and people with that training can go to a problem like an airline, and they know how to translate that problem into the math, and then software will take over and turn it into a schedule. I don't think there's a modern airline anywhere that doesn't use airline scheduling software. Now, deterministic optimization problems can be low dimensional, planning a path to a destination. It can be something high dimensional, like where should my facilities be to do my warehousing. Now, I'm mainly interested in sequential decisions, where you make a decision, then see new information. Then you make another decision, and then there's more information, and it goes on and on. Now, information that arrives after a decision is made is not known when we made the decision. Okay, which means when the decisions are made, we have to think about the information that might arrive. Now, some examples: inventory planning. I can make a decision for inventory. It might arrive right away, or it may arrive well in the future. Then I observe customer demands. Then I'm going to make another inventory ordering decision. Then I'm going to observe new demands, and so on and so forth. So this is a fully sequential decision problem. Let's take a trucking problem. I'm going to come back to this. Where truckload trucking, we're assigning drivers to loads, resources to tasks. Now, after I do an assignment at one point in time, I observe new loads and weather problems, and the driver doesn't show up. Then I make another assignment, and I get new information, and back and forth. Decision information, decision information. While we were testing vaccines, I had to make a decision about what dosage and who to vaccinate. And then I observed patient outcomes. And then I used that to feed into the next decision on dosage and who to vaccinate and test. And then, of course, finance, well, they do this at a sub-second level where they're trading assets and then observing price changes, and back to trading assets and then observing more price changes. And this goes on all day long. Now, you can take all of the decisions that we looked at before, and what I've done is for every one of these blocks, I've picked some information that arrives after you make the decision. Now, there may be multiple types of information arriving after you make the decision, but the idea is this is the information that arrived after you make the decision that was relevant to the decision. And when you have to make a decision planning into the future uncertainty, it explodes really quickly. This is a simple problem. This is what we know now. My initial decision is to buy, sell, or hold an asset. Then I'm going to watch the price go up, down, or stay the same, and then more buying and more price changes and more buying, and it explodes with dramatic speed. And this is a toy problem. There's only 3 possible decisions. So what I'm going to do is now let's roll up our sleeves and get into the problem of modeling sequential decision problems. Now, anytime you want to take a real-world problem and use analytics on the computer, you've got to go through the mathematician in between. Now, anybody writing out a deterministic optimization problem or a machine learning model knows how to write out their problem mathematically. It comes with the training. You know, you go out, you get trained in optimization, trained in machine learning, you know how to write the math. In sequential decisions, we don't have standard notation. There is no place that you can send somebody where they come back and say, oh, I know how to write that down. You can take a deterministic optimization problem and say, oh, I have uncertainty. By the way, George Danzig did exactly this for airlines in the 1950s. And yes, he blew it. Once you put uncertainty into a deterministic optimization, you enter what I like to call the jungle of stochastic optimization. And behind every one of these terms, every one of these is a field supported by at least one book, sometimes a number of books, like the field of optimal control. There's about 8 different notational systems, 12 to 15 different vocabularies and modeling frameworks. Every book has their own tools and their own classes of problems that they like to work on. So here's how to model a sequential decision problem. I'm going to make it very simple. At any time t, you have a state variable that captures what you know or believe. I may know something imperfectly. I then make my decision, any of those decisions we've discussed before, and then new information comes in, such as I've illustrated before. Every time you make a decision, you receive a contribution. I'll maximize contributions. You can minimize a cost if you like. That may depend on the state variable. The state variable might have a price in it or a cost. Decisions are made with a policy. That's how we're going to call the method for making a decision. And the goal is to find the policy that maximizes expected contributions. So this is the objective function. It takes a little getting used to. Now, let me stop and say, I can model any sequential decision problem using these 5 core components. State variables that consist of physical state like inventory, other information like prices or weather, and a belief state, which might be a probability distribution about how the market will respond. Decision variables like X that are made with a policy that I call capital X pi that depend on the state. The exogenous information is new information that comes to the system from outside the system. It could be somebody else's decision. We'll call that WT plus 1. The transition function. You tell me the state, tell me the decision was made, then give me the information that then arrived after the decision, and the transition function says, now here's the new state. Now, this could be a learning problem, and something the transition function is doing is updating my underlying machine learning model. And then finally, we get to the objective function where we're optimizing over policies, okay? Now, the way you evaluate a policy, there's 3 broad strategies. One is theoretically. Sometimes I can sit down and prove that a particular type of policy is optimal. Sometimes the best I can do is to say, well, it has a nice regret bound. And sometimes I can say, well, it's not optimal, but as n goes to infinity and I keep trying over and over again, I'll get the optimal solution. Now that only tends to work on relatively simple problems. Next step is numerical simulations, which range anywhere from something you do on a laptop to something you're doing in the cloud. And then you have to realize sometimes I just have to do it in the field. This has to be a live and learn type of thing where I'm optimizing through field observations. Now, let me take machine learning. Now, machine learning is an optimization problem. Right here, what I'm trying to do is to come up with a function, a statistical model. Maybe I'm trying to predict demand as a function of price. And somebody may come along, and this happened to me. I was working on a hotel revenue management project, and they had an expert award-winning revenue manager, and he liked to fit a line. Now, he would limit the prices. He says, look, limit the price to $80 to $120 a night, but in between it's a line. But of course, we want the best line. Now, somebody else could come in and go, no, it's not a line. It has to be some type of a curve. And there's got to be people listening to this talk that says, you got to hit it with a neural network. I'm just going to offer the caution that a neural network not only can give you overfitting, but it may not realize that the higher the price, the lower the demand. So our first step is coming up with this function, but it's going to come from within these 3 circles. It's going to be lookup table, parametric, or non-parametric. My challenge is to find the best class of function, and usually they have tunable parameters, and I need to optimize within the class. Now, to do this, I need this big data set. I need this set of observations of the input data X and the label or the observation Y. Now, let's compare machine learning to sequential decisions. In machine learning, I'm looking for a function, which is our statistical model. In sequential decisions, I'm looking for a function, we call it a policy. Machine learning needs a data set, sometimes a big data set. Sequential decisions, we do not need a big data set. That's the fundamental difference. We need a model of our physical problem. So now that can be hard to put together, but let's say that I have that. Let's poke at this problem of how do we search over policies? So designing policies. So let's start with, the word policy exists in the English language, but I still have people saying, what's a policy? What do you mean? So a policy is a method that maps a state variable into a decision, any method, okay? Now, here's policies in the English language. I'm up to 45 different words in English that all basically mean the same thing as policy. These are all words that in different contexts say, given this situation, here's what you should do. And if you'd like to, go to tinyurl.com/policies and decisions, and that's my spreadsheet. And if you think I missed one, please add it. I've had this on public websites and inviting people to make contributions. Now, it turns out that when you create a policy, there's 2 fundamental strategies. The one I call the policy search strategy. This is where we're looking for the best class of policy and the best policy within a class that works well over time. And the second approach is based on look-ahead policies, where I say, look, I'm going to make a decision, I'm going to earn something, and then I want to estimate the downstream impact of what I'm from that first decision, and then I want to make that first decision that optimizes the sum of the 2. So let's start with policy search, and I'm going to divide this and look ahead into 2 subclasses. So the first of the 2 subclasses is policy function approximations, or PFAs. And this is some analytic function that specifies what to do now, given what we know. So an inventory planning problem, I tend to do a lot of these. When the inventory hits a minimum, let's call it theta min, I'm going to order up to a theta max. If you tell me theta min and theta max, I've got my whole decision. Finance, buy low, sell high. I've got to know when the price goes below another theta min and sell when it goes above a theta max. But really a PFA can be any lookup table, any linear, nonlinear model. It could be a neural network, and it can be non-parametric models, any analytic model. Now, the second category under policy search, the second class, I call cost function approximations. And these are parameterized optimization models. So if you use Google Maps to find a path to a destination, the path looks pretty good. It may not be the super optimal path, but it's good. I'm willing to work with it. It says it takes 40 minutes for the trip. I also have to decide when to leave for the trip and how much time to allow. And I'm like, oh, I don't know about 40 minutes. There could be traffic. I'm going to add 15. And if I do this trip over and over again, I'm going to bump that up and down. In other words, that's going to be a tunable parameter. Grid operators planning our power for tomorrow, they're going to forecast demand, but then they'll add in reserves, mainly in case there's a generator failure. But if you've got a lot of renewables like wind, they also have to allow for the fact that the wind might dip below forecast. And if you're doing product advertising, okay, so all the e-commerce companies, you can say, let's say X is a product or an ad, and I want to say, if I show this product or ad, here's the estimated revenue. But that estimate is just an estimate. It's got uncertainty. And what I'm going to do is to take that number plus a tunable parameter times the standard deviation of the estimate. Now I just have to tune theta, but this is an optimization model because I'm going to pick the product X that maximizes this. Now, both the PFAs and CFAs, I end up with tunable parameters that have to be tuned. So instead of maximizing over a policy pi, I'm going to be maximizing over theta. Now, let me also point out parametric CFAs are widely used in industry in an ad hoc way. Pretty much dismissed by the academic community. You won't find this in any books. Okay, so now let's look at look-ahead approximations. Look-ahead approximations, I need to sort of look out into the future. And oh my gosh, yes, there's math in this talk. All right, this is as bad as it gets, but we're going to have to deal with this particular equation because this is how we look into the future. So here's the contribution of what I earn now, and that big messy thing is anything in the future. All right, so let's try to break that down because we actually do need to break this down. So I'm going to start in a state. This is what I know. It's a particular state, and I've got, let's say, 3 actions, but it could be much more complicated. I want to find the best action, but I have to consider what's going to happen next that's random, and I don't know what it is, so I have to take an expectation over it. And then I have all that messy stuff in the future. So let's break this down just a little bit. The policy pi is going to take each one of those square nodes. That's a state in the future. And I'm going to have to specify what decision I make when I'm in each of those states. Now, this is going to be the hardest part. I have to come up with that policy. It specifies what I'm going to make in every possible state in the future. Now, after I make a decision, something random is going to happen. And that's also very complicated, and I can't compute it, but I have pretty good ways to approximate it. So once again, there's 2 ways to break down the whole look-ahead approach. The first way, I can take pieces of that look-ahead and say, what if I can come up with that function? Well, it turns out this is what happens if I land in a state st plus 1. What's the value being in that state? Well, there's an entire field of research called Markov decision processes. By the way, a related field called optimal control, where they know how to solve this exactly. And if you can solve it exactly, you get an optimal policy. And guess what? This doesn't happen very often. There's not very many problems that you can solve it exactly. So another approach is let's use machine learning and estimate that value function approximately. Now, I still have this annoying expectation. I don't like having an expectation when I'm optimizing. That argmax is an optimization operator, and I don't like having an expectation inside there, but I could get rid of that using something called the post-decision state. So this is my book on approximate dynamic programming, and this allowed X to be a vector, and I can solve very, very high dimensional problems. And the last step is if you roll it all together and call it Q, now you're going to sound like you're in reinforcement learning, and this is a technology known as Q learning. Now, let me just briefly pause to say this does open some doors, and I'm going to come back to this problem of assigning drivers to loads. This is a very high dimensional. I can have hundreds. I can have thousands of drivers and loads. Now, after I assign drivers to loads, the future unfolds with uncertainty in high dimensions. And so this is dramatically harder than that decision tree, but if I use my value function approximation, I have the contribution from assigning drivers and loads now. That's an easy problem. I've known how to solve that since, I don't know, the 1960s and 70s. Now, if you approximate the value of the drivers in the future in the right way, this is a problem that's easy to solve in high dimensions. I can go to commercial solvers here and get an answer, 10,000 trucks, 50,000 trucks. So let me just hint. But at the same time, I have to say approximate dynamic programming is not a panacea. And you're talking to somebody who spent 20 years and wrote a 600-page book on approximate dynamic programming. It doesn't always work. Sadly, I'm going to say it usually doesn't work. There are certain classes of problems where it works fabulously. So what do you do when all else fails? And I like to say all else often fails. We have to go to direct look-ahead policies. Now, what I'm going to do, I'm using my same notation of state decision information, but I'm peeking into the future. And I'm going to do it with an approximate model. So I've put tildes on top of everything. I'm making a decision at time t, peeking forward to time t prime. So everybody's got to have two time indices. Now, there's a host of ways to approximate this look-ahead model. I can sample the information process using Monte Carlo sampling. I can use simplified sets of policies. I don't have to look all the way into the future. I can go out h time periods. I can restrict my state variables. I can simplify it and ignore some things. I can even ignore some decisions that I'm making. So there's a number of strategies, but this is art. There's no science behind this. Now let's say I can solve my look-ahead models. So here I am peeking out in the future, make a decision now. Roll forward, peek out again, make another decision now. Again, roll forward, peek out again, make another decision. Now, an example of this is our navigation systems. So here I am, I'm a Google Maps user. I'm up at Hartford, Connecticut. There's a company called Pratt & Whitney up there, and I'm working on a supply chain problem for them years ago. I'm going to come back to Pratt & Whitney, so I mentioned that here. But here it is, 4 o'clock in the afternoon. This happened to me a couple times when I'm planning my path back to Princeton, New Jersey, and Google takes me right through New York City. And I'm like, Google, you got to be kidding. I'm going to land in New York at 5 o'clock. Come on, you know, we can do better here. So it gave me an alternate route that I clicked on to go over the Tappan Zee Bridge, and it says it's 5 minutes longer. And I'm like, oh my gosh, yes, but I saved the risk of going through New York City. In effect, what I did was I solved my problem by approximating into the future. I used an extreme value of what might happen in the future. Now, looking ahead, the most classical look-ahead policy is deterministic. And in fact, there's an entire field called model predictive control. There's whole books. But there's all kinds of ways, and there's entire fields with entire books just on how to approximate the look-ahead. Robust optimization, stochastic programming, even approximate dynamic programming, and I'm going to illustrate that in a few slides, can all be used as approximate look-ahead strategies. So let's pause, take a deep breath. I've just covered 2 broad strategies for designing policies. The policy search approach that breaks down into 2 classes, PFAs and CFAs, and the look-ahead policies that break into 2 classes, VFAs and DLAs. Now I'm going to make the claim that any method for making a decision falls in one of these 4 classes and possibly a hybrid. You can mix and match. So I've given you a universal framework of how to model any sequential decision problem. I've now given you a universal roadmap for designing policies. Okay, and I think this took me a very long time in my career, especially given that I, like many academics, stayed focused on the VFA approach. But if you work on wide enough sets of problems, you're going to find you need all 4 classes of policies. Now, I'd like to ask everybody, please, when you have a minute, go to jungle.princeton.edu. Scroll down until you see this picture. Print it out, pin it to your desk. This in one page is a thumbnail sketch of the universal framework on how to model it and the 4 classes of policies. Okay, trust me, everybody watching this presentation makes decisions over time under uncertainty. This is the universal problem. Now, so I talked about that we have the policy search strategy and the look-ahead strategy. Academics love the look ahead. They're more sophisticated, they're more complicated, you can publish papers, but you go into the real world and not that many people are using those strategies except for deterministic look aheads. Policies in the policy search class are the simplest. And so this is what you're most likely going to see used in practice. But I learned to tell my students the price of simplicity is tunable parameters, and tuning is hard. Anybody who does machine learning and has to do hyperparameter knows the pain here. This is just hyperparameter tuning. So here's a little energy example. Here I can take energy from a wind farm, and it's variable and reasonably unpredictable. Anytime I need, I can pull power from the grid. I've got infinite amount of power for my needs, but it's at very random prices. So Texas, typical prices is $20 a megawatt hour. In Texas, it hit $9,000. I'm trying to serve a relatively predictable demand. Now, here's my Tesla Megapack, where I'm going to store energy to handle variations and smooth out the fluctuations. What I did was I created 5 variations of this problem by tweaking the data in a certain way. And then I made 5 policies. The first 4 of these are from the 4 classes: the PFAs, the CFAs, the VFAs, and the direct look aheads. And then I created a 5th class, which is a hybrid. Now, the number in the cell is the percent of how well you did with perfect information, and I made each of these 5 classes work best for different data sets, all in the same class of problem. And I claim that there's a lot of people out there who think, oh, no, the only way to solve this is with method X. That's how I was trained. And they don't realize, I think you actually need all 4 classes stunningly on even within a particular problem application. So let's go back to bridging machine learning and sequential decisions. So our first class of policy is the PFAs. That's everything in machine learning: lookup tables, parametric models, non-parametrics. When I'm using PFAs for identifying policies, I'm doing basically the same thing I'm doing in machine learning. The only thing is I don't have a big data set. I have a system model, but otherwise all the same tools. But it's only one of the 4 classes. You're going to need the other 3 classes, the CFAs, VFAs, and DLAs, each of which are optimization problems, modified optimization problems. So this is our roadmap for sequential decisions. By the way, I have an online book, tinyurl.com/sequential decision analytics. This is a book I wrote for an undergraduate class. It uses a teach by example style with the exception of 3 chapters. Each chapter focuses on a particular problem. Look at the table of contents. You'll see the basic outline of those chapters are always the same. The problems have been chosen to illustrate all 4 classes of policies. And by the way, I highlight to some degree uncertainty modeling. Now, this is the major book that I'm working on. It should come out next year. It's a work in progress, but it's pretty good shape. And if you go to castlelab.princeton.edu/RLSO, you can download the current version. Do so fairly soon. I'd love to get some feedback. I have to submit it to Wiley in September, and at that point I'll have to take it off the internet, but grab it now. I'd love some feedback. I'm working on the final chapter. There's a lot of editing to do, but it's readable. So let me give you now some illustrations. So I'm associated, I retired from Princeton after 39 years, as John said, and joined a startup, Optimal Dynamics, that licensed all of my software for the trucking industry. And there's a white paper that I wrote, and if you go to tinyurl.com, Decision Analytics in Trucking, we lay out the math of what we're doing. And even if you don't read the white paper, it's about 12 or 13 pages, just look at the section headings and you'll see that we're using all 4 classes of policies. And this is a white paper with math. This isn't just hand-wavy, fluffy stuff. Now, I'm going to give you a little tour through the white paper. So here we saw our truckload problem using value function approximations. Now, let's say that we have, this is a time-space network. Time goes left to right, space up and down. And this vertical blue rectangle is all the drivers and loads at time t. And then I have the value drivers in the future. So what's in blue is my optimization problem, and it's not too large. So I can simulate it into the future, and I can run this simulation over and over again. And this is how I learn the value functions. Now, Optimal Dynamics has been running a number of studies with various trucking companies. So here's from 11 different companies. The first iteration, the value function sold 0, so that's like a myopic policy. And you can buy commercial software that uses a myopic policy. So this is commercially sold software. Now, as you train, after about 15 train iterations, I've got overall performance improving by anywhere from 15 to over 40%. So these are real numbers. These are actual real improvements. We're making more money. We're getting drivers home. We're picking up loads on time. Now, let's look at these two problems. Now, the one on the left, everybody hopefully should understand. That's the game of Go. That's our big breakthrough. Reinforcement learning has been all through the newspapers, being able to do this, and it's a major achievement. Let's take a look at the problem on the right. This is a 5,000 trucking company. Every truck driver has a 15-dimensional attribute vector, giving where the driver lives, his full hours of service, which is fairly complicated for anybody in this industry. I know his home domicile, I know his equipment type. I have to juggle about who gets what driver load and what's the best driver for this load. And then I have to think about which load should I cover and how well do I do in the future. Here's one of the problems we have to deal with. Shipper calls in and says, hey, I've got this load to move on Friday. The problem is it's not Friday, it's Monday, and I have to say yes or no now. Now, I don't know where my drivers are. I have to figure out, do I even have a driver to cover the load? If so, is that even a load I would want to move? Is this going to help my network profitability? And does it help the driver get home? These trucking companies have real problems hiring drivers, if you've been reading the newspaper in this area. So we're going to go back to that crazy, messy function. I tweaked it just a little bit. Here's my approximate policy in the future. Now I have two types of decisions. I've got to assign drivers to loads, and I'm going to use my same VFA-based policy. I've estimated the VFAs offline, so now I just have to simulate them, but I still have to do load acceptance in my look ahead. So I'm trying to design a load acceptance policy, but I still have to do load acceptance in the look ahead model. I'm going to do something simpler. I'm going to make some simplifications. This will actually be a mixture of a cost function approximation with tunable parameters and a touch of PFA. I'm going to then simulate this policy into the future. Now, I've replaced my expectation with a risk metric because now I'm actually going to say, what is the probability I cover the load? Now, here I'm simulating 20 times in parallel. This is all done on the cloud. So each one of these is me simulating my VFA policy. And for every load that I'm looking at for load acceptance, I'm going to say, for each of the samples, did I accept or reject? So let's say there's this one load that was accepted 18 times out of 20. So that's a 90% acceptance probability. Now, this is a CFA policy, which I can put into a simulator and roll forward and roll forward. And so I can then tune parameters. Here is one of our largest customers that we've worked with. Now, this carrier has a very large base of loads, but these loads are from its brokerage division. And what we're doing here is we're going to say, I want to pick and choose from the loads in the brokerage division. There's about 15,000 loads in the brokerage division. Which ones do I want to move in my main network? Well, this says on the left-hand side, there's 5,000 loads, probability 0, doesn't work, stay away from them. There's 3,000 loads, 3280, where it said, oh, wow, this is a total win. 20 times out of 20, I like that load. And then there's 10,000 loads where the probability comes up anywhere from 5% to 95%. Now, maybe I'm going to pick a cutoff, 0.8, and say, all right, everybody above 0.8, I'm going to keep. Because, by the way, I make a lot of money when I cover these loads with my main network rather than through the brokerage division. Now, this is where we've tested this policy on 10 different real companies. Carrier A is a very small carrier, 60 or 70 trucks. We ended up saving about $2 million a year, which is a lot of money. The two bigger carriers are much larger. We're saving 20 to 25 million. This is big money for a truckload carrier. This is improving profits by about 15, 20%. So this is causing quite a ripple in the industry. All right, now optimizing a big truckload operation. All right, that's fairly complicated. I think it's quite an achievement compared to, say, playing Go. Let's take it a step further. So I mentioned I was up working with Pratt and Whitney, and so we were working on modeling their supply chain. They have over 1,000 components from 600 suppliers, lead times up to 300 days. Here's a simulation, an animation of their simulation. of their supply chain. And it's very complicated. In the 1990s, somebody actually tried to optimize a supply chain using deterministic optimization, and that went badly. How in the world do you optimize something this messy? And the first thing you realize is I don't have one decision maker. I've got decision makers all through the supply chain with the different vendors. Well, every single decision maker I'm going to replace with a policy. And I'm going to go in there and model just the one decision maker and tune it so that he's doing the best he can, because in fact, he's just running his own operation. So let's imagine that I'm that decision maker in the middle, and I have people upstream of me making decisions that impact what I'm doing, and my decisions will impact people downstream. Now, that particular problem isn't very large and isn't very hard to solve. I just have this problem of designing and tuning the policy. Now, we have this running at Pratt & Whitney as a simulator, and even I would say, well, gee, it's a simulator, what is it proving? Well, let's take a look at Norfolk Southern Railroad. We worked with Norfolk Southern for 10 years. Norfolk Southern runs around 2,000 locomotives. This is one complicated operation. So what we're going to do is break it down. Here we're modeling it over time. Each of these slices is about 4 hours. And then we're going to divide the network into their freight yards, which is really how their decisions are made. They optimize within each freight yard. But I have to know that a decision in one freight yard has a downstream impact, just like my supply chain. I'm going to use feedback learning to learn these value functions and do it iteratively, and over the iterations learn these value functions. This system is in and running at Norfolk Southern, has been running since 2006. This paper, which did win an award, but academic awards, or I don't know, I guess they're sort of worth what they are. I love the fact that it's actually in and running. It's being used for strategic planning and tactical planning, and this is how they do real-time execution for the locomotives that have to get home to shop. And if you want to ask about this, go call Clark Cheng. He's still working at Norfolk Southern. Very proud. This is something that is a nice proof of concept. Now let me give you a real-world inventory problem. Here I've got an inventory in Atlanta. I've got to plan my inventory. And you say, how do you plan inventory? Well, you go back 60 years and everybody will say, use an order up to policy. Inventory goes below one level, order up to another level. Okay, every book, you can hire major consulting firms, they'll say this. So let's say somebody tells you, well, I've got this cargo ship coming in with some inventory, and there's also some more inventory coming in on this freight train. How does that change what I want to do now? Wait a minute, no, I've got 3 cargo ships coming in. One that'll arrive in 4 days to LA, 1 in 2 weeks, and 1 in 3.5 weeks. Now, how does that change my decision? Now somebody just told me I've got a big storm headed for LA. It's going to shut down operations for several days. Probably my freight is going to be delayed for a week. Well, I have a decision I can make. I can put it on air cargo and fly it in, or at least just enough to tide me over until the cargo ships arrive. Or maybe I can reroute the cargo ship through Vancouver and put it on the train, but I'm going to lose some time and trains are slow. I'll put it on trucks, maybe even bypass my warehouse. Now, tell me, how do you put all of it? This is very real world. This is absolutely happening. How do you put that in a base stock policy? Well, instead of having 2 parameters, you could have each parameter depends on the state of the system. So you have 2 functions. Cool. What's in the state variable? I've got all the arrivals by ship and air freight. I've got weather forecasts, port delays, land transit times, maybe even have oil prices and currencies. In other words, that's a complicated function. I'll be honest, I don't have the faintest idea what it looks like. This isn't something where there's a big data set that will teach me to it. I have to do policy search. I don't actually know how to solve this problem, but I do know how to build that model. This is really just a giant simulator. Yes, I have to design that policy within the policy, the sigma, the pi tilde, but I've got my roadmap of the 4 classes of policies. And no, I'm not going to use a stochastic look ahead in my look ahead policy. I'm going to look at something else that's simpler. Now, when you go to choosing across our 4 classes of policies, there's a trade-off between how hard it is to design the policy, like that state-dependent order up to policy. That's really hard to design. I mean, I honestly don't actually have, oh my gosh, I'm really smart, I know how to do that. Down to the stochastic direct look aheads that are hard to compute, but they're actually easy to design, okay? And then there's a spectrum of everywhere in between. So obviously this whole trade-off is very problem dependent, But at least if you understand all 4 classes of policy, you'll know I've got the complete roadmap. So I want to now close. The whole field of decision analytics stands on 3 academic fields: optimization, machine learning, and simulation. Each of these fields have well-defined communities, common notation, established tools. If you want to hire students, there's lots and lots of academic programs producing this. But the world of sequential decisions is a mess. There is no field. There's 15 distinct communities. Everybody's got their own notation, different tools. No single one of these books would tell you how to handle any of those problems that I've described. I'm going to claim that my 2 books are a starting point, and I'm going to say what my books are doing is just what the other books do in deterministic optimization, machine learning. Instead of teaching one tool, it's going to be a broad-based education covering everything, because when you get the world of sequential decisions, what you tend to get is people highly specialized in just their area of expertise. So now I'm going to turn and hope the audience listening to this can help me. We need to bring pressure on universities. I think this is work that probably needs to go on inside engineering. So if you want to solve a supply chain problem, you're going to find it in a business school. Business schools, the MBA students are not the right group of students. You need people with mathematical expertise, but not, advanced math. I think you need the same math that you need for machine learning. Okay, I think there's actually a surprising amount of overlap, and that's why I keep comparing this to machine learning. If you go to castlelab.princeton.edu/SDA for sequential decision analytics, that's a web page that pitches my vision for this field. Thank you very much. I've really enjoyed this opportunity. I'm looking forward to the questions.
So thank you, Professor Warren. That was a fantastic presentation. I feel like we just scratched the surface.
Yeah.
And I don't want to spend much time. We have about 6 minutes left for questions, and I would like to hand over the Q&A to my colleague Piyush Kumar, and he's going to run the Q&A for us.
Thank you, John. Hi, thank you, Warren. Very fantastic talk. I really enjoyed, sort of like how you passed out, the places in the industry where sequential decision making happens, and how does it actually frame to the fundamental mathematical problem. So we have a few questions from the audience, so we can start there. So Sharath from the audience asks, do you have an intuition of where each type of function approximation might work well versus not? Example, what kind of problems are amenable to reinforcement learning versus stochastic optimization versus more classical formulation of MDPs and predictive controls?
Okay, well, understand when you mention all those other fields, those are just different classes of policies. So rather than referring to the field, let's just refer to the 4 classes of policies, because optimal control and MDP and reinforcement learning, these are all working on sequential decision problems. Okay, so what we have to do is pull back from saying, oh, but what about MDPs and whatnot? So if you go to chapter 11 of the grad level book on designing policies, I do have a section there where I'm trying to do my best to give guidance on how to do that choice among the different classes of policies. Okay, by the way, I've also tried to have conversations about what is reinforcement learning, and that's turning into a messy thing. If you just say, look, the problem we're working on is sequential decision, and then we have the 4 classes of policies, now we're just choosing among the 4 classes of policies. But I'll tell you, that's the toughest thing. You have to have some intuition about how each tool, the characteristics of each tool computationally, and then what the characteristics of the problem. I'm going to say it's exactly analogous to somebody machine learning. Say, well, how do they know whether to use a lookup table or a parametric model, and if so, which parametric or non-parametric? They're making that same choice. It's just richer.
Yeah, thank you, Warren. So, just sort of like broadening that question a little bit, what kind of intuition sort of like can we bring in, right, when we talk about these 4 classes of policies? Let's say, I have an industry problem. Let's say I have a problem in energy where I'm simulating energy grids, and I want to make decisions, in matching the generation to the demands, right? So how can I sort of tap into my intuition to select what kind of policy or what combination of policies?
Well, so I spent a number of years running an energy systems lab, and every summer I would go down to a meeting the Federal Energy Regulatory Commission, FERC, would run a modeling workshop. And everybody knew that renewables were coming in and there's uncertainty, and this one field called stochastic programming took over the workshop and said, we've got the answer, it's called stochastic programming. And for a decade, all we could hear about was stochastic programming. Well, I was off on the side building a simulator that really matched one of the big operators called PGM. And then I looked at what PGM was doing, and I had this aha moment that says, oh my gosh, what PGM is doing is really good and better than what all the academics and the industry researchers. And this is where I invented the policy called cost function approximation. It came from watching PGM. And basically they said, let's take a deterministic model and put in tunable parameters to make it work better under uncertainty. And I just went, oh, that's so much better. Now, how do you come to that conclusion? It's a lot of staring at a problem. Some problems scream at you, but like I've got problems where value function approximations are fabulous. They're just great. I'm telling you, just give me 5 minutes and I will tell you how to change the problem so that the VFAs don't work. For example, that load acceptance problem. VFAs don't work. You have to do a look ahead. How do I know it? Gut feel. I just have no clue how to do a VFA. But again, if you have any background in machine learning, lean on the same type of intuition. It's just going from a smaller set of functions to a bigger set of functions. But chapter 11 in my book, I do take a crack at talking people through how to choose the policy.
Thank you, Warren. So we have another question from Adit. So Adit asks, when designing policies, is there any value in revisiting old policies in light of new information? Perhaps to do better credit assignment, may not reduce regret incurred by past decisions, but might provide good learning for future decisions. Do such.
So in other words, revisiting the class of policy. So let's take my energy example, where I made all 5 policies work best, 4 of them being each of the 4 different classes. So in other words, all you have to do is have the nature of the data change. So let's say you're doing a supply chain and COVID hits. That's a very different world. Very possibly, a simple order up to inventory policy was working fine up until COVID hit. And all of a sudden you need a look ahead. You have to do a look ahead because order up to policies are great for stationary problems, but now you've got this big hiccup. When you have highly evolving problems in the future, you really need a look ahead. And so, but I'm going to tell you, it's gut feel. I think this is going to be one of these areas where I'm doing my best to help people to provide guidance, but the simple fact is experience is what really counts, just as it does in machine learning.
Wow, thank you very much. So I think we're just at the hour, out of time, and I'd really like to thank Professor Warren again for spending time with us. I feel like we could probably spend all day discussing this really fascinating subject. So anyway, so our extreme pleasure to have you, Professor Warren, and all of the and thank you for the audience for the the questions and submitted. And just like to announce, please join us for our next lecture, which is Tuesday, April 20th. It's AI for Science, a Revolution in the Making, and our speaker is Anna Kumarda from Caltech, and look forward to having everyone join us again. Thank you.
Thank you all.